Today I'm excited because we get to hear about programming the Kinect, which I think ought to be fun. And we've got our very own Shaun Tonstad. I didn't butcher it, did I? Okay, like I've done before. But in any case, if you remember, Shaun didn't come from here. He came from Colorado. And before I kind of said, well, why would he come here? Well, he has some good reasons, in particular family, right? In fact, there's one person here from his family. So he has 2 daughters and a lovely wife. And again, the type of living here is very good for a family lifestyle. So even though we do technical, there are other things that are important. Well, Shaun had worked at Lockheed Martin. And most recently, when he came here to this area, he's worked at LRS. And he's also worked at Jar Dogs. In fact, I remember seeing him one time at a conference, or not a conference, but in a class by a guy by the name of Billy Hollis. So if any of you have done some things with design and things, you still see him at Microsoft conferences. And it turns out he's working for a guy that I also had seen at that same instructional class. So it's kind of funny, in this area, everybody seems to know everybody and things tend to cycle around. Well, right now, Shaun is working at Progressive Impressions International. I had to look at this scratching and see what it is. And he has recently moved from Jar Dogs, where he was kind of the uber programmer and chief architect, and now is doing something completely different. But we have the opportunity today to hear him talking about the Kinect. And like I said, I'm very excited, so welcome, Shaun.
Thank you for the great introduction. I'm really happy to be here. And this is always fun for me, and Kinect in general is something that is very special for me because I feel that there's a need to bridge the gap between science and education and in the next generation to share with them all the excitement that you and I have for our work, engineering, and writing software. So the title of today's talk is Learning Microsoft Kinect. And as Mark alluded to, I have some background working with Xbox 360 and other titles. Just to give you a little bit of background about who I am, I started work at Lockheed Martin. I wrote software for satellite ground stations, and I did that for a short while, and then I started a software consultancy specializing in 3D visualization. And so some of what you're going to see here today, you can see that background. It lends itself. I've shown some examples with XNA and 3D graphics. From there, I worked at Jar Dogs and helped them build version 1 of their patient portal using Azure. And it's the largest healthcare deployment inside Windows Azure. And so I have a background in cloud computing and 3D graphics. And currently I work as an architect for Taylor Corporation, which owns PII, which Mark mentioned. So some of you know some of my exploits, things that I've been working on. And I just wanted to give some of you an update. And first and foremost, I just want to thank everyone for their support for the Kickstarter for the game called Warcraft. And it was essentially the concept that you can take building blocks made out of materials that you harvest, and you can build anything you can imagine. And it uses Azure on the back end for bringing the players together. And this was, for me, this was really great to see all the interest and the passion in this project. And so I just wanted to give everyone an update and thank you. And I'm actually taking these technologies and the 3D graphics, and I'm actually rolling that into a Facebook game here that runs on Facebook, Windows RT, Windows 8, and also the browser. And it's a unified architecture that bridges both Silverlight and Metro. And we'll see 3D graphics of that from the Kickstarter project. So I'm really excited, and that may be perhaps a topic for a future talk. And what I'm looking for, though, is some closure. Perhaps a successful Kickstarter. I want to see this brought to market, and then I think that would be great subject material for a future talk. And we can talk about the trials and tribulations of raising capital and bringing an independent product to market. But enough about that. The goal today is to talk about Kinect therapy. I first got introduced to Kinect working at Jar Dogs, building a physical therapy application using the Kinect. And what our goal was, I was approached by the CEO, and he said, there's all these great things going on in wellness and in the healthcare space. How can we build something that patients can bring home with them and help improve their quality of care? And to that, what we came up with was this concept that we could actually send Kinects home with patients and give them guided physical therapy. And that guided physical therapy is actually sent from the physician's workflow from their electronic health record system. And that EHR then, the physician orders, basically they'll say, okay, for this given patient, they need to do a series of stretches or exercises, and that information would then be sent to the Xbox 360 and displayed. And we gave a successful presentation of that technology at several healthcare conferences. And so what you can see here, this is actually a great example of Kinect, and I'm actually tracking a person's heart rate in real time and counting the number of repetitions. You can see the depth texture on the left side of the screen, and then an animated avatar that walks patients through the process. Now, ultimately, in this case, this was a product that wasn't brought to market. We couldn't establish a return on investment for something like this. I mean, the Kinect sensor only cost $150, but it's definitely a great example of what's possible with the Kinect. So here's an overview of what we'll talk about today. I'd like to start with the history of the Kinect and give you some background on how we got to where we are today. I'd also like to cover the Kinect hacking scene. It is very alive and well, and it's the lifeblood of what has made Kinect so popular. We'll talk about some of the technical capabilities of the Kinect and what you need to get started. I'll give you a walkthrough of some of the technical terminology and the things that make Kinect work, including depth buffers, and we'll do a short, brief introduction to the coordinate system, and then we'll dive deep. And we'll start writing code, and our goal for today is to build a simple Kinect application that tracks skeletal animation and will respond to our movements. And lastly, I'll give an example of a commercial application that leverages Kinect, courtesy of Taylor Corporation, and it's something that I developed for them. So the Kinect history, it was originally created by a fellow by the name of Ziv Zalewski in Israel, and with a group. And he's actually an interesting character. He actually is also, he's credited with the creation of 50 different patents, and one of those also including a heart rate sensor that works optically. Can you imagine a heart rate sensor that looks at the tone and color of your skin and can gauge heart rate? And so that was in 2005 that he created that, and Microsoft worked with the company PrimeSense and purchased the rights in total. And in 2009, that began as what is known as Project Natal. Along with similar Microsoft code names, Natal is a city. It's located in Brazil, and Natal means birth. And it was the birth of a new idea, Microsoft's beginning foray into a new user interface in the consumer sector. So they released a beta version of Kinect in 2010, and that's when I began using it and started working on the physical therapy for jar dogs. And it's largely unchanged since then. They've made improvements to the API, and we'll talk about some of those. And they officially released the SDK in June of 2011. So by 2012, there are more than 300 companies that are not gaming companies that are building serious applications using Kinect. Everything from the medical field to, we'll look at examples of a musical orchestra run through Kinect, and there's just so many fantastic examples. And I'd like to show some of those to you today. And so there have been some changes in the industry now. So Kinect's been around for a couple of years. How many of you here are familiar with Project Glass? Maybe a show of hands. And good, how about Leap? Has anyone heard of Leap? So a few of you out there. And so there's a convergence now. People are realizing that there's a need for a natural user interface. Natural means that it's a new way of working of something. I use my hands. Maybe I communicate with it. It's very natural. It's very like Star Trek, the next generation. I can just say computer, right? Xbox, play Netflix. Well, so clearly this is an important stage in the computing evolution. And so Google's Project Glass began in 2012. Glasses that you wear that have a meta layer that you can interact with the world around you. And just recently in May of this year, Leap released a device that's called the Leap. And what it does is it tracks movements in your fingers, very fine motion movements, so that you can actually draw with a high level of accuracy through 3D space. You can type and communicate by moving your hands, and you can do it effortlessly. And the device is small enough in form factor to be integrated into consumer devices. So this is our future. This is where we're going. I expect that 10 years from now, some of us will not be typing as part of our daily job. And we've heard about these predictions for years. It's been on for 40, 50 years. But now we're actually seeing the physical fruit of that research. And I expect great things from Leap. And in some ways, it's the intellectual heir to Kinect. And we'll see that by the end of this year. So the Hacking Kinect movement started like this. Some guy said, wow, Kinect's pretty amazing. Let's build great stuff with it. And then Microsoft responded and said, Microsoft does not condone the modification of its products. And we'll work closely with law enforcement and product safety groups to keep Kinect tamper resistant. And there was a public outcry. And naturally, people were saying, we're just trying to build something amazing, And it was around this time frame that I had this idea that I wanted to build an autonomous robot. Why not, of course? So it was kind of weird because the Kinect, it wasn't necessarily known in the hacking movement. And I wanted to figure out how you would do this. And I thought, well, naturally, you're going to use, IR and bounce it off so you can actually see the room and the world around you. And so I actually did a search to see if I could find something that would produce a depth field or something similar, raw data. And you can. Those devices did exist prior to the Kinect, but they cost $7,000. And so the price of a Kinect is $120. And so this is a big difference. And that's why now today we see all the success that we've had in the Kinect hacking movement. So they reversed their position 2 weeks later, and the rest is history. On KinectHacks.com, there are over 500 high-quality, unique demonstrations of Kinect hacks. Think about that, 500 different ways of demonstrating what you can do with the power of Kinect. So before we begin into the technical details, I'd like to give you a demonstration of what some people have accomplished using Kinect. This was actually the video that caused my boss at Jardogs to come and talk to me and say, hey, we've got to do some amazing stuff with Kinect. What can we do with it? Now, this fellow here, what he's done is he's used CG imagery to basically reconstruct, or CT imagery to reconstruct a skeleton. And it's just a simple polygonal model, and it's being animated based on the position of his body. OK, here's another example. I think this is something that many of you have already seen. And this is actually really simple. By the end of today's demo, you'll be able to accomplish the exact same thing that you see here. This is easy. This is child's play. This is 10 minutes of programming. So the doctor, he's all prepared for surgical, and he can't touch devices. It's in a clean room. But he can use the motion of his hands to guide the computer. And this is my favorite example. And so there's an organ behind him that he's, I don't want to say playing, but he's moving through a MIDI sequence by controlling it with his hands. So my mother-in-law has graciously volunteered herself to be basically a test bed for Kinect animated Christmas lights. And so I would personally like to have lights where you're walking down the street at night, and then as you walk, the lights kind of flash as you walk down, and you can use your hands to orchestrate the music. And she said, oh, sure, that sounds fine. She has no idea what she'd be getting herself into. This is an example of Kinect fashion. So I'm able to try on clothing in real time, and I can switch that clothing. Very shortly here, you'll see a color map of different colors. Those different colors represent tension on the clothing, where it may fit too tight or too loose.
And a database of thousands of body scans is employed for statistical extrapolation. The tension maps here represent where the garment is tight on your avatar in red.
Yeah, she's good, huh? She's good. Yeah.
Touching in yellow.
So you can see there where there's tension. I guess that's normal for women. That makes sense.
We can do away with tension maps, which are intuitive and cool for techies, but not for the everyday shopper. Instead of trying to figure out tension maps and what that means for
so they're calling it a tension mask.
Lively avatar.
All right, I don't know. We're gonna skip past that. All right. All right, and this is my all-time favorite. This is virtual reality. It's basically telepresence using a robot and a Kinect to pet your cat at home.
Virtual reality mode on. Okay.
So it takes them about 20 minutes to get to the cat. So we'll skip past that for a little bit there.
Okay. Brush, please. Thank you. Okay. Now let's go forward. see. Can I get any closer? Maybe not.
Isn't that great? Look at all the things you can do with Kinect.
I think I need to get closer.
The cat loves it.
I think I can get a little bit closer. See, look down. Okay, that's as close as I can get. Brush.
Brush. So let's talk about what the capabilities of Kinect are. There's really three major categories for Kinect. It does skeletal tracking and avatteering. Avatteering is the concept that basically I take my skeleton and I take my movements and I imbue that with a third-party object. Maybe it's your avatar, an Xbox 360, or it's the robot controlling the brush. And so we do things like we track the position of joints. We track and we infer whether or not a particular joint or hand or limb is visible or not tracked, and it does so at a rate of 30 hertz, 30 times per second. It also does facial recognition, and this is probably one of the most up-and-coming features for Kinect that we find interesting. It basically looks at your face and it finds features, eyes, eyebrows, your smile. You can see if you're smiling or you're frowning, and then it can actually take that content and then it can basically map it to a polygonal model and texture map it all in real time. And we have a demo of that we'll show today. And then lastly, it does 3D audio and speech recognition. There are actually two sensors on the Kinect on each side. And what it does is it triangulates your position based on where you're located. And so you could actually have the ability to say, okay, so let's say someone over here speaks, and then it actually is tracking a skeleton, then it knows who the speaker is. So let's talk about what you need to do to get started. If you're on the Microsoft platform, you're working with C#, C++, or DirectX, then the best way to get started is to download Visual Studio. You can do 2012 Express for C#. You can download the freely available Kinect SDK and also the Kinect Toolkit. SDK has the bits you need to talk to the Kinect, and the Toolkit has a great collection of examples that you can use to get started. And then you really have two choices. You can work in WPF, you can work in XNA. I prefer XNA Game Studio. You can actually go headless. You don't need to have a visual representation. You could create, if you want to, a kiosk that uses Kinect. There are alternatives. You don't need to use the Microsoft stack. You can actually also use Open Kinect. And when I started working with Kinect, Open Kinect was a viable alternative. It had a lot of great features. I will say this, though, that the .NET Kinect APIs have come a long way. And in terms of feature parity, there's a lot you can do with the Microsoft SDK you might not be able to do with open source alternatives. That being said, Open Kinect supports a variety of languages, including Python, JavaScript, and Lisp. So there was a new SDK that was released. Newest features include seated mode skeletal tracking. So do you remember the physical therapy example that I showed all of you? That wouldn't be possible. You couldn't have a participant sitting down in an anchor man pose, if you will, because it wouldn't be able to properly track you. You actually had to stand up and it had to see all four limbs to begin the tracking sequence. That's not the case anymore. They've improved that so you can sit down and show your limbs. It also includes joint orientation. So one of the things that I was trying to do is I had the avatar, and at first I thought, you know what, I want to have an avatar that mimics what I do to help people. And I'd bring my hands up, but there would be no orientation. And so it's really important to demonstrate orientation using the hands. It also supports near-range mode tracking within 16 inches, and that's kind of what Leap does. It's the idea of using your hands and fingers to interact, and you can do that at near range. There's actually two models. There's an Xbox 360. So that near mode capability, basically within 16 inches, you can basically interact and use gestures, and that only works with the Windows version of the Kinect. And if you have an Xbox version at home, you can certainly write code and use it, but you can't use the near field mode. So everyone's seen the Kinect. Here it is. Well, let's talk about the physical hardware. There's an IR projector. It shoots out, basically, it shoots the beam out, and there's a picture of it that I have on the next screen here, across the entire room. So right now, all of you are being basically irradiated with a harmless level of radiation. And then it also has an RGB camera that will basically, it's optical, and then the IR sensor, which picks up the IR projection. So this color buffer that you see here, it's basically a 32-bit pixel image, probably things that you're used to seeing, 4 channels, 0 through 255, a byte for each channel. And what's special about this in my mind is that it's actually agnostic to presentation. It's basically just a straight-up array of bytes. And that's how people have been able to use Kinect in open source and third-party platforms, and even in JavaScript. Here's the depth buffer. It's a little different. It's actually 16 bits, so only 2 bytes. Bits 1 through 12 represent distance in millimeters. And then they do something really interesting. The actual identification of the player is actually encoded in here. So bits 14 through 16 represent the player. And you'll actually see that in our demonstrations today as color-coded presentation. The players will be color-coded. So 2 to the 12th is 4,096, so that's the actual maximum range of the Kinect sensor, 4,096 millimeters, or gradations of depth. So I'd like to talk briefly about how the Kinect works. Now, I'll be honest with you. I read several white papers, and I understood about 1/10 of them because they were all, 90% was mathematics. But here's what I gathered. In addition to writing software for Kinect, I wanted to present you a mechanistic understanding of how the Kinect works. And so the first thing it does is it captures this depth image using that IR sensor. And if you were to stand in front of the Kinect, what you'd find typically is that there's a wall behind you, or open space. And it turns out that's actually the space where it can't see any further definition. And so it turns out it's really easy to find people because things reflect off my body, and they don't anywhere around me. And so typically when players engage the Xbox 360 or Kinect, they're the object closest to the sensor. And that greatly reduces the search space. And so what it does then with that object that's in front of the sensor is it tries to infer body parts based on looking at each pixel individually. And so you guys know that we're at a place in time where we can do object recognition based on patterns. So here it's taking black and white pixels or color pixels, and it's basically looking for patterns. This is a hand, right? This is an elbow. This is a head. And it's actually running that processing on every single pixel, looking at all of its nearest neighbors to try to identify whether or not something's a hand. So this color map that you see here, you see the red is actually representative of someone's right hand. Greater shades of that orange or red color represents greater probability that that, in fact, is your right hand. And you can see, so they've color-coded each of the different joints and body parts of the body. And then from there, it moves to the third step that you see here, where we look for the computed midpoint, or the center, if you will, of that clustering of pixels. So you see at the top there, that centering of red pixels represents the midpoint, or theorized midpoint for the head, and then that gets mapped to a skeletal model where it provides X, Y, Z points. The Z, which is your depth, comes from the distance that was recorded from the depth sensor. So that makes all perfect sense, right? But many pages of mathematics. So further, what they did is they built the system, and then they had to actually train it. And if some of you may be familiar with the terminology in expert system, right out of the gate, they needed to perfect it. And so what they did is they actually created 500,000 frames of motion capture data to run their system against to gauge accuracy. And they tested it with over 100,000 different human poses. Just a gigantic volume of data. And what they did is they looked at people, everyone from different sizes, people who are big, people who are small, tall and short, and people of different ages. So if you look down there at the bottom, second image from the left, you can see that we have people of different gaits. We have an older person and we have children. And they trained it to all this variability. And they also trained it against basically accessories, purses. So one of the things that I did when I worked at the physical therapy application is that I introduced the therapy band. And I was really surprised at how well the Kinect sensor worked, recognizing what were my limbs versus what was the therapy band. It would basically ignore the therapy band. And the way it did that was because in its gigantic search space of different types of models, there was nothing valid in which I could have a stream or basically a horizontal or vertical beam that would be valid. The only time I could get it to recognize the therapy band as a limb is if I hid my arm and then hung a therapy band down the side. And then I had a wavy, wiggly arm. So it's very accurate. So before we start writing some code, there are a few basics that we want to talk about, and that's the coordinate system. Initially, DirectX started as a left-handed coordinate system. And that was based on the idea that 0, 0, or your origin, is in the top left corner of the screen on Microsoft systems. That's great. That's how Microsoft did it. Everyone else, including academia, did a right-handed coordinate system. And that's the way it was for a long period of time. Now, Kinect is actually a right-handed coordinate system. And it's only until recently that the DirectX API, and they basically have divorced themselves from a coordinate system. And now you can be right-handed or left-handed. That's how they resolved that issue. And a lot of legacy games use left-handed coordinate systems, and a lot of newer work, including academia, uses a right-handed coordinate system. So let's see if anyone knows. This direction right here, what axis would this be? Any takers? Just shout it out. I don't care. OK, we've got an X. OK, so OK. And this direction here, Y. OK, and we go positive going this direction. Now, how about Z? So I'm going, if I'm pointing this direction, is that Z positive or Z negative? So that's the difference between a left-handed and a right-handed coordinate system. And a right-handed coordinate system is Z is going to be positive going this way. So the data structure that Kinect uses, here's an example of a skeleton. And so what we get back, and you'll see this in the code, is a skeleton frame. Skeleton frame contains one or many skeletons. One or many skeletons have one skeleton has a position, and a skeleton has many joints. And each joint has a position, and then each position, or each joint has a tracking state. Tracking state says whether or not it can physically see that particular joint or whether it's inferred. And that's the magic of what they've accomplished here, because they have so much existing motion capture data that they've trained the sensor against that they actually now can say with some certainty whether or not something that it cannot see is actually still there. So you can actually take your hand and you can move it behind you and it can still see it. So there are a variety of skeleton joints: spine, head, shoulder, hip, and suffice it to say, this is what you program against. You take the X, Y, Z coordinates, and this is how you write your code. OK, so let's begin by building a Kinect application. And I'm very excited to do this with you together. So we have a couple goals, though, first, that we're going to try to accomplish. First, we're going to initialize the Kinect device. Second, we're going to capture a display buffer. And that's the color buffer. That's basically the RGB camera. And then we're going to capture the depth buffer. And then we're going to do some simple computing with the player arm. And we're going to check to see if the player's arm is over their head. And depending on how things go, we'll see if we can make that more complex. And what I want to tie together here is how simple this is. So remember the physician who was in the operating room and the gestures with his hands. At the end of this demo, you'll be able to accomplish similar functionality. OK, so first let me run an application and show you what we have. We have a blank screen. So this is a empty initialized XNA application. That's cornflower blue. It's the default setup. We haven't done anything special. And so this is our starting place. We're starting from, in terms of Kinect, Scratch. And I won't really talk about XNA much because the topic of today's talk is Kinect. But I will explain some things as we go along here. So in this really simple vanilla XNA application, we have some things here that I'd like to call out to you. We have two texture objects: a color frame texture and a depth frame texture. And so that corresponds back to the things you've already seen. Now you know what a color texture is. You know what a depth texture is. You have an understanding of what those are. Here they are in the code. Now, if you're working in the WPF world, you could treat these as bitmap objects. In XNA, they're texture 2Ds. So we talked about initializing Kinect. I'm going to go ahead and drill down into this code here. I've wrapped some of it so that it could be a static singleton that's thread safe for various reasons. But I want to actually drill down into this method here and show you how we initialize the Kinect. So there's a static method or a static object that has a collection of Kinect sensors. You can actually tie together multiple sensors. And I'm not sure what that exact number is. I think you can have up to 4. And so what we're doing here is we're referring to the first connected sensor with the subindex here. And then we call sensor.start. That's it. It's that simple. And then we check for Kinect status. Is it connected or is it not connected? And so now we basically have initiated our access to the sensor and the SDK. And now what we do is it's event-driven. And to think about, why is it event-driven? Why can't I just grab my picture? And the reason why is because that device there captures data at a different rate than which your code might be running on. If you're running a game, you have a tight loop of processing. And so what you do is you hook the event. And the reason why is because the the color the color buffer could be captured at 60 frames per second, but the depth sensor could be captured at 30 or even a variable rate. And so that's why we hook the events for it. So I'm actually going to drill down into that. So when a color frame is ready, what happens here? Well, remember, we talked earlier about the format for that data, and so you get a simple byte array that you work with. And this logic that we're doing here is we're saying, OK, take this array, and I'm going to go ahead and copy it and make it generally available. And I'm going to show you some other code where I actually convert that into a texture. But it's here in this place that you would actually make the conversion and put that in a bitmap image. Similar thing with a color frame. It's a little different. Remember, we talked about that you have 11 bits, and of those 11 bits, that identifies your depth. And then you have the remaining bits that represent color index. And so this logic here basically runs through. And it's just basically some bit shifting. And this particular example is actually available in the toolkit. And so I'll be honest with you, I did not author this, which is good. There's some complexity here. But this is something that you would do if you're working with WPF or XNA. So we've initialized our Kinect sensor. I'm going to go ahead and go back now to the part where we actually update state. OK, so in every XNA application, two major concepts. You load content, textures, models that you want to display, and then you update state and draw. So updating is the process that I'm changing state in the 3D world, regardless of what's actually being drawn. So it's a lock time step, right? If you play Halo at home, it's updating the game's internal state at a fixed lock step of 60 times per second. Maybe you're in an area where there's a lot of monsters and the animation's slow, it's slowed down, but internally though, the motion and the physics and kinematics processes at a locked rate. And so within that update method inside XNA is where we do our computation to see if someone's raising their hand, lowering it, and those types of movements. And then the second thing that we do in XNA is that we draw. And so this is my first step here in the tutorial. And so the XNA Kinect has been initialized. And now what we're going to do here is we're going to take that texture and we're going to draw it to the screen. And so let's go ahead and do that here. And so this will be an example of the color buffer. So what I really want to impart here is how simple it is to display the content from Kinect.
Somebody had to do that.
So it's pretty straightforward. I mean, nothing too magical here. Let's kick it up a notch here, though, and let's show the depth buffer. OK, so here we go. Here's the depth buffer here. And then I actually need an audience, someone to participate. OK, Mark, you want to come up here and stand on the X right there? No, you have to stand up in front. No, it's tracking you, Mark. So see, there's the player index. It's tracking two people. Here, both of you stand up. Yeah, both of you guys, if you could stand. It's already tracking you. So go ahead and stand side by side. And then come a little closer here. There we go, red and blue, so it's actually tracking two players. Let's bring another person in. Alan, could you stand in front of him? Kind of between them here. Now, notice how Alan was white when he initially started. White is basically the closest value that you can display. If you move beyond white, then it stops tracking you. And so you can see it's tracking 3 people, which is fantastic in real time. How does the Xbox do this? So when they initially made the Kinect sensor, they did all the processing on board, on the Kinect. And they said, this is great, but then it was decided, you know what, our per unit costs for production are so high, we need to offload this to the Xbox. And the Xbox is highly threaded. It has, I think it's 3 cores for the Xbox 360. And so they actually have plenty of processing power. So all this processing actually occurs either on the desktop if you're using Windows or the Xbox 360. Sorry, guys, you probably thought you were done, but you're not. So now, here, Alan, if you could be our test subject. You guys are done. Now, Alan. OK, so what I want to do here is, Alan, go ahead and bring your hands out. And here, hold my phone. Sorry, well, kind of improvising here. So now take that phone and pretend like you're signaling an airplane for SOS. So take the phone and kind of guide it towards the sensor. There you go. Now look at that. Can you guys see? Go ahead and hold it. See how that black obstruction there? That's actually the IR bouncing off the crystal display or the display of the phone and basically moving away from the sensor. So Alan's reflecting that. And so you can see that as indicated by the dark square there. Thanks, Alan. So it's not perfect. And all that jaggedness that you see is actually the result of the IR bouncing off different objects and different things. You know, it's not static. and there's a high degree of variability. Okay. All right, so now we've showed the color texture, the color buffer, and the depth buffer. Let's actually do something meaningful now. Let's actually write some code. So I mentioned before in XNA, there's the concept that you do all your physics processing inside the update loop. And that update loop runs independent of your ability to draw things on the screen. So that's the perfect place to do this. So first thing we need to do is know whether or not we can actually see someone. And so there's a state object here called state is tracking skeleton. And so let me show you what that actually is. So here inside, let me show you where that happens. And so the Kinect sensor fires asynchronously. Let's go ahead and look. So I didn't actually show you what happens though for the skeleton stream. So remember I showed you the code for the color buffer when that was ready asynchronously, and I showed you for depth. But let's look at the skeleton one here, and we'll drill down into that. And so we're taking this event, skeleton frame ready event args, and we're going to call open skeleton frame. We call open on it, and we wrap it in a using clause because it implements iDisposable. So it can cause a memory leak if you don't clean it up. And of course, that makes sense. I mean, basically, this is a wrapper for unmanaged code. It's highly performant code. It's written in C++, and they've been nice enough to give us a C# wrapper to it. And so the first thing we can do is from that skeleton frame, we figure out, well, how many skeletons are there? That's skeleton array length. And we get a collection of skeletons. And then what we do is we take that unmanaged data and we copy it to a local buffer, and we iterate through those skeletons. And the first thing we look for is skeleton state, skeleton.tracking state on the right here, equivalent to tracked. Now there are other options. It could be tracked or not tracked, and position only. And so tracked means that we can physically see that particular player, and I just basically wrap this information and store it in an object. Because what I want is I need to be able to have the drawing portion of the application see the last known good state for Kinect. So you have these two things that happen asynchronously, right? You have rendering, which is asynchronous, right, on the graphics card. And then you have the Kinect firing information giving us asynchronously. So someone has to be a constant. Something has to be a static. And I chose Kinect data for that reason. OK, so state is tracking skeleton is actually calling that skeleton, am I tracked? So let's go ahead and run that code here. And I need another volunteer. Lee? Because you just, I can see the passion. OK, that's what happens. All right, so it can see you. So that's excellent here. So see if you can walk. Try to walk. I think it's actually tracking Mark Lovick, too. You can see the blue there? So everyone get out of the. All right, we'll fix it. Is there anyone on the ceiling? I can't see you up there, so that's good.
What if I get real close? Can it see me if I get right here?
Yeah, I can still see you. That's I like the jacket.
But it's not tracking me, though, right?
No, I think it is.
There we go. All right.
We'll.
I've seen this movie.
All right, so a really simple example here is, let's say, OK, what if I want to detect when my hand is above my head? So when someone's asking a question, imagine that we built this automated system, and someone raises their hand, and the teleconference camera zooms straight to you, and then you begin talking. So let's look at that example here. All right, so looking at the code here, are we tracking a skeleton? Yes, we are. We look at the joints that are available to us. We take the hand right, and we take the head, and in position Y for the hand is above the head. So you guys probably thought this was complicated, right? Look how easy that is. It's child's play. Really simple code. Can everyone read the code OK? Is it visible? Because I can make it bigger? OK. So let's go ahead and run this and see how it works. OK, I can't see anyone. That's great. So we need someone from the audience to volunteer. Any volunteers? Very good. You guys don't even have to get up. Look at this.
Oh, it's got to see the person, obviously, before it can.
It does need to see a person. You guys, I didn't code this for extra skeletons. Whoever's skeleton 0 wins it. So that would be. Yeah, okay, so congratulations, you're skeleton 0. This is excellent. So we have some really great examples. We'll get to some more complex stuff. So it's great to see it working. Okay. So now, let's say this. How do we write the code then to figure out whether or not someone is clapping, bringing their hands together?
If hand right and hand left position are the same.
If they're the same, that's good. Now, that's it. Lee is right now, but remember the accuracy, right? There's jitter.
Right.
And so think about how you might do that. And you're exactly right. So you take the difference, right? Because in case someone's doing this, take the difference and then just take the absolute value. So let's go ahead and do that. So I'm going to provide this code example to Alan so we can put it where it needs to be or wherever it needs to be so it's publicly available. And all of you can run with this and build the next great Kinect hack. Okay, excellent. And so, I had a tape measure that I intended to bring, and I think I left it at home because I wanted to show you how accurate the Kinect is. But I'm going to go ahead and see if I can usurp that from you, Mark. And okay, good. So does it have me? Okay, it has me. And I had this tape measure at home, and what I did with the tape measure.
Is that in meters?
Yes, that's correct. It's in meters. So this is 1 meter, and I took the tape measure, and it was accurate within 5/100ths or 1/20th. Is how accurate it was, which is fantastic. That's just really amazing. So you do have to normalize it and use that skeleton position. Well, maybe you don't. I thought you had to. And what's kind of neat here is that as I move further away, see how so that's the maximum range of sensor definition that you can see there. There actually isn't a wall right here. That's just the extent.
Yeah, you said 4,096 millimeters. It should be a little over 12 feet, right?
Yes. Yeah, that's right. Okay, so before I move ahead, are there any questions that I can answer? Yes? It's cool. See, this is now a short story here. My daughter actually helped me test the software. And so this next application I'm going to show you was something that I built for Taylor Corporation. And they're involved in the business of creating media and basically printing and materials. And for them, it's really important to have messaging get out to customers. And what they asked me to do is they said, Shaun, can you build for us a augmented reality application that potential customers can interact with? And what I'm going to show you is what we came up with. But I had a helper, though. My daughter, Sabine here, helped me test the software. And I was concerned about its ability to work with people of different sizes. And so we worked together here. And we'll call on some folks from the audience to test that software and make sure it works. OK, so I'm going to go ahead and switch now to different presentation. So this is a good stopping point for us. So this is the demo here that I'd like to show you. And bear with me here. OK, so I'm going to go ahead and run. OK, excellent. OK, so we need another volunteer. First, I'm going to demonstrate and walk through the software here and explain it. OK, so I'm standing here on the X. And so for this particular company, what they wanted was they wanted to draw people in to their trade show and have people approach them and say, what are you doing here? What is your company all about? And they would have an opportunity or a chance to win a prize based on the success outcome, which is configurable. It's actually fixed. As soon as you pull that lever, it already knows whether or not you were going to win or lose based on that fixed percentage. For today's presentation purposes, your odds of winning are very high. And everyone's a winner. So, but again, what we're going to showcase are the things that you've already learned today to show you how simple it is. So there's my color buffer on the left side of the screen. I'm inside XNA right now. I have a 3D model. And it's telling me, hey, raise your hand. And it knows that because it can see it. Now, what if I hide my hands? So it can still see my mark. It's still seeing you. You have to go to the back of the room. All right, I'll get a little closer for you. Is it me now? Get up here, then you can do it. But you lost, though. See what happens? The 1 in 30 chance, and you lost, buddy. All right. Oh, shooters. It's seeing you guys, and I'm not tracking for multiple skeletons. Okay, everyone pay attention, it's working. All right, it says I can't see your hand. Now I can. And it says, well, raise your hand. And so that's that concept where it's, it can't see my hand, but it's inferring the position. So I'm going to go ahead and raise my hand. Okay, now it's above my head, right? This is what we've done today. Now it says pull the handle down. Now if everyone watches the handle, watch what happens. You see, it's actually tracking the position of this joint in XYZ space, and it's looking at that y-axis, right? And so when I bring my hand, and when I bring my right hand below my hip joint, that's when it fires. So now it says press the stop. I bring my hand out, and so it's looking at, now it's looking at the Z position, right? And so I change that Z value, and I'm hitting the buttons. That's really all I have. So I'm done here. I've got in the slides that I'll provide to Alan, I have some references for the papers and ways to contact me for further questions. There we have it. Okay, thank you everyone very much for your time, and I appreciate the enthusiasm. Thank you.